Okay, so this review problem is a short theorem. Prove this formula for the union of three events. To do this problem, we'll recall that the formula for the union of two events goes like this. Probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. Okay, so what I'm going to do is everywhere I see an E, I'm going to replace E by A union B. So everywhere I see E, I'm going to replace by that. So over on the right hand side, I have the probability of A union B plus, that's to be determined, minus the probability of A union B. Okay, and everywhere where I see an F, I'm going to replace that by C. So now the left-hand side matches the left-hand side over here. So everywhere I see F, I replace by C. And so I have used the union rule here for this. Okay, now how can I simplify this? Well, I can apply the rule a second time to this. So the probability of A union B, that's the probability of A, plus the probability of B, minus the probability of A intersect B. Plus the probability of C comes along for the ride. Okay, now what do I do about this? For this, I will apply De Morgan's laws. And one of De Morgan's laws says that that A union B then intersects C. That is the exact same thing as A intersects C union B intersects C. Now this is something that we discussed in class. Let me describe this step here in a little more detail. So what we're saying here, and maybe the best way to do this is by just drawing a quick picture. So let's take a look at the three events. So here's A, here's B, here's C. So A union B intersects C. So I have to be in A or B, so that's this part, and I have to also be in C. So that's going to be this part of the Venn diagram right here. So I am in C, and the shaded part is in either A or B. Now notice that the shaded part also is A intersects C is this part. So what I just shaded, or what I just outlined, that's A intersects C. And B intersects C is this part right here. And of course, that is exactly the same thing as the part that I just shaded. Now, we described the proof of this in more detail in class, so I'm not going to describe the full proof of it here, but the gist of it is I'm applying De Morgan's laws to change this intersection into a union. The intersect C basically distributes, kind of like the ordinary distributive law for addition and for multiplication. Okay, so let's continue. Now, you'll notice that things are starting to line up here. So probability of A matches this, probability of B matches this, plus probability of C matches this, minus the probability of A intersect B is here. So the first four terms match up what I want to end up with. And so the hope is that this will match the last three terms over here. So minus. Well, I apply the rule one more time. The probability of the first plus the probability of the second minus the probability of the third. So A intersects C, intersect B intersects C. Now let's distribute the minus sign. The probability of A plus the probability of B plus the probability of C minus the probability of A intersect B minus the probability of A intersects C minus the probability of B intersects C. Then we have minus, minus, plus. So minus a negative becomes a plus. Okay, so this is saying the points have to be in A, and in C, and in B, and in C. Well, I said C twice, so that's repetitive, that's redundant. And so the net effect is that this set is the same thing as a set of all points that are in A and in B, and in C. And so we end up with the statement of the theorem as desired. So to do this proof, we used this union rule twice, and we also just had to use some set theory of first De Morgan's laws over here, the fact that this intersection distributes over this union in much the same way that multiplication distributes over addition when you multiply out with the distributive law. And there's one other little catch over here, that this is A intersects C intersect B intersects C, which is the exact same thing as A intersect B intersect C.